All right. Well, by my count, this is week 3 of statistics that we're just starting into. So just think about that, folks. We are already a 1/6 of the way done with this class. It is definitely flying by. The goal today, obviously, we'll talk homework questions first. The first few homework sets are due tonight at midnight. So if you haven't been playing along, this is definitely the time to start playing along. But we'll talk a little bit about any questions you have on homework. And then after we do that, we're going to just keep moving on. We're going to just sort of review a little bit what we talked about last time with the measures of the center of data, right? Mean, median, mode. Talk a little bit more about spread of data. Now we use standard deviation to do that. So after a little bit of review of that, then we're going to dive into the next chapter, chapter 3, which is about probabilities. And for some of you, that may be brand new information. A lot of you have maybe seen some of it before, but we'll talk probabilities and start seeing how the phrasing of things, the wording that's used, is supremely important. Anyway, so that's our plan for today. But before I do my bit, let me go ahead and open it up to questions from the homework. Are there any that you would like to look at from any of the sections?
Yeah, so I found the questions.
Okay, what would you like to see, Willie?
Well, I'm thinking maybe we just didn't go over this yet. I don't know.
Can you tell?
Yeah, question 1, chapter 2, measure centers and spread.
Okay. We'll go look at it and see if we can figure it out. Anything else? Any other ones that people would like to talk about? Have questions on?
Can we go over, I know we touched on it a little bit at the first meeting, but can we go over outliers too?
Sure.
Yeah, I have the question up right here because I'm listening and doing my homework at the same time.
Okay, which section is that? Can you tell me which?
It's sets? Chapter 2, box plots. It's
okay.
Do you need the question too?
Just which number? Yeah.
Yeah, I was actually I wanted some help on that assignment too, if that's
okay.
not too
hard.
Yeah,
no problem. We'll definitely go look at that.
It's question 8.
Okay, I'll put that on the list and we can definitely go take a peek at it.
Okay.
All right. Any others? And if as we're going, if right now you're not really sure, but as we're going, something pops up and you're like, oh, wait, what about? Feel free to chime in and ask, type it in the chat box, something like that. And if we've got time, we'll go and look at it, okay? So let me go ahead and share my screen with the assignment page. And we will go look at these two. So I'll actually start with the box plots question, saying it's the first of the, or it's the one earlier in the list. But I'll definitely get to the one about measures of center and spread as well. Come on, computer. There we go. All right, so question number 8. All right, so here is a, it says the 5-number summary of a data set. Now, I know I never called it by this name, but think about what the 5 important numbers were for a set of data. When we make the box plots, box and whiskers, what are the 5 numbers that, what do those 5 numbers represent?
The 48 would be the minimum, so 67 would be the maximum, okay. 50 would be the first quartile, and then 64 would be the third, I think, and then 56 is the median.
Good. Yeah, that's exactly how to read these. So if you just have those 5 numbers, that's the same as actually having a box plot, right? It just, instead of drawing the picture, they just give us the numbers. And honestly, to a mathematician, I would actually prefer having this or giving this, because it's a lot easier. It's a lot quicker. I'm lazy. Most mathematicians are lazy. All right, so we want to see now, given this information, how do we determine if it's an outlier? All right, so outlier just means it's really kind of far away from the box, right? So does anybody remember how you tell specifically if something's an outlier? What do we have to determine in order to find out how far away we can go?
The inner quartile range.
All right, so we need the, yep, exactly. So we definitely need to calculate the inner quartile range, which is the difference between the first quartile and the third quartile. All right, so what would the interquartile range be for this set of 5 numbers?
14.
Good, 14. So we knew our quartiles were 50 and 64. So we just take those differences and it's 14. You know, I'm going to share a whiteboard here so I can draw some stuff here instead of just say it, because I think if you see what's going on, it might make a little bit more sense. All right. All right, so our numbers, let me just go ahead and rewrite them. So they were 48. I'll even draw the picture. So that was 50. Out here was 64. And then we had 56 was in here. And then 67. So that would be what the picture would look like given those 5 numbers. But again, the interquartile range, the IQR, is the distance between those quartiles, which will be 64 minus 50, or 14. Okay, so that's where that, excuse me, where that 14 came from. All right, so cool. We got our interquartile range. So how far away do you have to be for it to be an outlier? How far away from, how many interquartile ranges do you need to be away for it to be an outlier?
1.5, right?
Yep, it's 1.5. So what we're going to do is we're going to take this number and we're going to multiply it by 1.5. And what that's going to give us is 21. So we're an outlier if we're 21 away from the quartiles. So if we go out from the third quartile, go bigger by 21, or we go 21 from the first quartile and go smaller, that's what would be considered an outlier. So to answer this question, we just have to either add 21 to the third quartile or subtract 21 from the first quartile. Okay, so Ali just put in the chat box, why did I multiply by 1.5? And you're going to love this answer. And I say love, but really you're going to hate this answer because that's the rule. That's how we determine what an outlier is. They're defined as values that are 1.5, more than 1.5 interquartile ranges away from the box. All right, so it's a cuz. All right, so if we think about these in terms of the, we'll add it to it, this will be 85, that's my 64 plus 21. And when I subtract from it, what is that, 29, I think? So for 85 or bigger, that's considered an outlier. If we're 29 or smaller, that's also considered an outlier. So here's my question to you guys then. For this data set, do we have any outliers?
No.
Yeah, and it's actually a pretty quick no, because we know the biggest value is 67. I mean, it's actually really close to the third quartile. It's not very far away. And the same thing with the 48, the smallest value. It's not even remotely close to 29. So you can always get a sense of that as well, about are there any outliers, by basically looking at the size of the box. Think of the interquartile range as telling you the size of the box. And then looking at those whiskers and seeing if those whiskers extend down 1.5 times as long as the box. And so since these whiskers are short, we know we don't have any outliers. So this is probably going to be a pretty good data set for us in terms of hoping to get a representative sample.
I have a quick question.
Sure.
So say given maybe more numbers in a data set, and there were two numbers, like just add 29 and 85 onto that number set. If there were two or more clear numbers that were outliers, would you still recommend? I know like it would be clear that they were outliers, but for you, would you still check to see if it was an outlier or?
Okay. So a couple things about this, Carson. So, but that's a good question. So first of all, remember that these 5 numbers are not the necessarily data points, right? It isn't like we just have a list of 5 numbers in our data set, right? This came from a huge list of data.
Got it. So
we ran the numbers.
You pulled it.
Yeah, it's a summary, basically. These 5 numbers are a summary of the data set. So I just want to make sure that that's clear. And there are only 2 numbers on here that you are guaranteed to actually be numbers in our data. Which of those 5, the 48, 50, 56, 64, and 67, which of those are data points in our set?
50 and 64?
Not the 50 and 64. Because quartiles can happen in between data points.
Oh, okay. The minimum and maximum on the 5 numbers then?
Yeah. So the ends of those whiskers, the minimum and the maximum, those for sure are in our data set. I can tell you with 100% certainty that on our list of data, there is a 48 and there is a 67. I also know that the rest of our data is somewhere still between 48 and 67. But in terms of what their specific values are, I don't know. But I do know it's the median of that group. The median is 56. So there could be a data point that's 56. But 56 could also be the average of the data points on either side, right? And then same thing with 50 and 64. Those might be data set points, but they also could be
the averages.
67
and 56 and 48 and 56. Would that be what the averages of that, or just the averages of 48 and 50?
It'd be the averages of the 2 data points on either side of that list.
Got it.
Right. So like, okay, so this could be, let's say, the list for our data. I'm just going to, I have no idea if this is actually accurate or not. I just need to make sure that, I mean, it's probably not accurate, but I need to make sure that, let's do another 62, 66, 67. Okay, so like, let's say that this is our data set. And we go and we make a box plot of it. Box and whisker. Okay, so here's our minimum. And there's our maximum. Right, so that just gave us the endpoints of our whiskers. We go for the median. So we have to find the value that's in the middle. So I made this so that there are 9 data points, so that my median is going to be a data point. and it would be 56. It's the value that's in the middle. There are 4 above it and 4 below it. Okay, so then when I go and I find my quartiles, I have to look at like the top half of this, the top 4, and find the median value. Well, the median of the top 4, since there are 4 of them, it's going to be halfway. It's going to be the average between these two, which would be 49 and 51. Its average is 50. So there's Q1. And then I do the same thing to get my Q3. I have to go halfway of the top 4. So I don't have a data point, and I would need to take the average of 62 and 66 to get my Q3. So like here is a data set that would be represented by this box and whisker plot, or these 5 numbers. But it's not the only one by any stretch of the imagination. I could make a list of 100 elements so that I get this exact same picture. But this is kind of keying in on what I was saying, that sometimes these numbers can be actual values in our data, like the 56. It actually was one of our data points. But 50 and 64 are not on our list. So we have to be really careful with these 3, the quartiles and the median, because they might be on the list, they might not be on the list, we don't know. If all you give me are these 5 values, you don't know that they're there. Okay. So that was the first thing I wanted to bring up, just to clarify on your question, Carson. But then the other one, you said like, okay, let's say that there was something really far out, right? So like, let's say instead of having the max of 67, I'm going to change that max to 102. So think about what changes now on our box whisker plot. The min's still the same. The quartile 1 is still the same. The median and the third quartile are still the same, because I have the same number of data points, so I'm still looking in the same spots on my list. But the maximum is now very different. So this whisker
skewed way to the
is
right.
Going to be super long out here to like 102. And so what I know, again, because all I know from this set of 5 numbers from my whisker plot, the only thing I really know is where that end one is. What this can tell me, because since this distance is so long, I know that this 102 is an outlier. We can run like we ran the numbers and we saw, oh, if we have something bigger than 85,
because like the range of the I guess, what would that be? Q3 of 64 would be Q3. It would it be from, because the range of 102 to Q3 is so great.
Yeah. If you look at that interval, that length, it's more than 1.5 times the length of the box. It's more than 1.5 of those interquartile ranges. And that's how I would know that there for sure is an outlier. Is there only one outlier? Well, obviously in our list that I made, yes, there's only one outlier, but there's the possibility that there are more, because I don't know all the specifics in here.
Mm-hmm.
I don't know all those specific numbers. I only know some of where things lie. So, but basically, if you want to just look at a box and whisker plot and see if there are any outliers, look for the lengths of the whiskers.
Okay.
If the whiskers are more than 1.5 times the length of the box, you for sure have outliers. And you can have outliers just on one side and not on the other. You can have outliers on both sides. It totally depends. So with these graphs, you might have one short whisker and one long whisker, kind of like what I have drawn here. You might have 2 long whiskers, which tells you, oh, I've got outliers on both sides, right? Or you could have 2 short whiskers like we started with, and we know that we don't have any outliers. All right. So
Okay.
for those
Thank
of
you
you
for clearing that up.
yeah, you're very welcome, Carson. So for those of you who had questions on that, does that make a little bit more sense? I forget who was that, Ashton, I think, who asked about that.
Yeah, it makes sense. Thank you.
Okay, you're welcome.
I also had one more question. I forgot what the spread was for a box plot.
What do you mean the spread?
Like, this question's asking, like it just says what is the spread, and I'm looking at a box plot for question 1.
Oh, okay. Probably, and I'm not 100% sure on this because sometimes people use different terminology, but I'm going to guess that that means the basically from minimum to maximum value. So from whisker to whisker.
Oh, like, so just the range of the whole entire.
Yeah. So like in our original one where we went from 48 to 67, I think I would interpret spread as 19. The data is spread out from 60. If you take 67 minus 48. All right, so let me now jump back to, yeah.
I'm not sorry for interrupting you. I
Okay.
tried doing that actually. Like I just found the range. It was incorrect.
All right. So you said you were looking at question number 1?
Yeah.
Oh, okay. Now it makes sense. So this just said, what quarter has the smallest spread of data? So that means basically which of the quarters are the smallest in length. So in my picture, that would be the third quarter.
Mm.
Right?
I'm talking about question B.
I know that.
Oh, I'm sorry.
No, that's okay. So it's the third quarter. So then it says, what is that spread? So it's asking you, what is the spread of the quarter that has the smallest spread?
Okay.
So in this one, the answer would be 11. Because there's an 11 difference between the median and the third quartile. All right, so hopefully that works for your homework problem because it's the spread of that specific.
Yeah, that was perfect. Thank you so much.
Okay, you're welcome. All right, so let's pop back and go take a look at, yes, it's fine. Sorry, I have a whole bunch of windows open that are covering other windows. There we go. All right. So let's go take a look at that question from the measures of center and spread. And we'll see if we can. So Will, you said it was number 1 from that set. Is that right?
Yeah.
Okay. All right, measures of center and spread. All right, so here's question number 1. So we got data set that's right here. So we want to find the mean, the median, and the standard deviation.
Well, I kind of have a different question for that one, for question 1.
Okay. Let me try a different one. Okay, let me just throw in some numbers here and be completely wrong. I mean, if I end up getting any of these right, I'll be completely shocked because I'm just randomly punching in numbers. Oh, I got 0 out of 1. Okay, let's try a similar question. Does that look more like it?
Mine asks about like the mid-range as well.
Okay. Let me keep going here. Man, I'm doing horribly. 0 to 0.
That's the one.
Okay. All right. So we've got highway mileage for a sample of 10 different models of a car company can be found below. Okay. So find the mode, the mid-range, the range, and then estimate the standard deviation using the range rule of thumb, and then now use technology, find the standard deviation. Okay. I know for sure we talked about standard deviation, and again, it says use some technology. I would use technology, but if you want to, you can use that formula. Remember that one that was the square root of the sum of the x minus x bar quantity squared divided by n minus 1, right? So you can use that or put this into technology to get your standard deviation. How about mode? Because we talked about that. What does mode mean?
The most common value.
Okay, so that's the one that shows up the most. All right, so what's the mode for this one?
31.
Yeah, 31. It's the only one that shows up twice. There's a 31 and a 31. Okay, let's pass mid-range for a second, but find the range. So range, again, is, this is what I thought maybe Carson meant when he talked about spread. So range is just what's the difference between the smallest value and the biggest value, right? So what is that for this set? You see the smallest one is 24. Biggest one looks like it's 49. Right? So that would be 25, right? So we know that our range is 25. And then we didn't talk about the range rule of thumb. So let's come back though to mid-range. So what do you think mid-range means?
Maybe the range of one of the quartiles.
Okay. That's a good guess. What does mid suggest to you?
Half.
So half, middle, right? Mid just sort of gives you that context of somewhere in the middle. Okay. I'm going to real quick share a whiteboard. I just wrote down all those numbers so that I can access them. But let's go back to that whiteboard. Okay. So thinking about mid-range is all about kind of like the middle of this thing, right? And you can actually, if you go and you look in your textbook or online, do a search, you can find what mid-range means, right? But it's basically that idea of it's the range to the middle, right? So instead of doing the entire difference, it's the average of the big and the small. All right, so it really is, it's a mean of the top and the bottom. So if we were to look at ours with our set, give me 1 second here, I gotta clear this. All right, so in terms of our data points, we had the low was 24. The high was 49. right? And so we already saw that the range was, what we said it was 25. So the mid-range, it's the low plus the high divided by 2. So a way to think about this is the average of the max and min. So we just take those two values and we average them. We get our mid-range. So let's see, that would be 73 divided by 2, I think is 36.5. So what this is giving us is an estimate for the median or the mean, or basically the center of the data. Let's think about this. If we were doing a box and whisker plot of this thing, we knew that the high was 49 and the low was 24. By doing this, the mid-range, we are finding the value that's exactly half this distance. So if we were to cut that distance in half, let's say that's right here, this is our mid-range. Because it's halfway between 24 and 49. Now, does that mean that it's going to be in the middle of the box? I don't know. Does it mean that my median is going to be there? Not necessarily, right? But at least it's giving us an estimate for where that middle might be. Okay, so mid-range, basically just, that's what it sounds like. It's the middle of the range. It's the halfway in between the max and the min. Okay, so then that leaves the range rule of thumb. All right, so that guy I definitely did not talk about. All right, and this one, to be perfectly honest, I don't even know what that means in terms of the range rule of thumb, or at least I don't know it by that name. So let me just pop up a Google window here and see what they're talking about, because I probably know it as under a different name. Okay. So the range rule of thumb is basically says this, that the standard deviation is about 1/4 the range. So let me go ahead and write this down. So the rule of thumb, I guess it's the range rule of thumb, is that the standard deviation is approximately 1/4 the range. So since we already have the range is 25, all we got to do is divide that by 4. And so we get that the standard deviation is approximately 25/4 or 6.25. And again, that's just a guess. That's totally a guess. But it's based off of information we already know. I don't know if you guys remember, do you remember that thing called Chebyshev's equation or Chebyshev's rule? It's okay if you don't remember exactly what it says, but you remember we talked about it. And it talks about how much data is within a certain number of standard deviations. And it's basically making use of that, right? We know with Chebyshev's rule that we know that about, regardless of the distribution, right? Regardless of how it's distributed and what it looks like, we know that about 75% of the data is within one standard deviation of each side, or sorry, two standard deviations of each side, right? And so that 75% is how we're kind of getting to that idea that if you want to find 75% of this, you can kind of back it down and go with, okay, around 1/4 of the range. If you take 1/4 of the range on each side, it comes from Chebyshev's equation. So for this one, if you just want to make your guess, it's going to be around 6.25. So let me go back to that window and we'll, where is that window? There we go. Oh, no. I apologize. This is all, there we go. All right, so now we're back to here. So let's put in the stuff that we know. So the mode was 31. There are 2 of those. The mid-range, so the approximate center, what did we calculate that was? 37.5, I think. The range itself was 25. So we know that's around 6.25, and I have 0 clue what the actual standard deviation is, but we'll go with something around it. Let's see how we do. Oh, I didn't get the mid-range right. Did I type that in wrong?
I think it was 36.5.
Okay. Well, anyway, well, let's see if that's what it actually was. Oops, 6. Okay. Thank you for that, because I need all the points I can get, obviously. So that's how you can find these. And notice how we can find those 4 things without technology, right? It was really adding, subtracting, multiplying, and dividing. It was stuff that you could do by hand if you needed to. And that's why it's kind of nice to have those. In terms of the actual standard deviation, let me try another one. Yeah. How many more submissions do I get? I should be about done, right? All right. I'm done trying to just guess on it. But anyway, you can use your technology to find out what the actual standard deviation is, and it should be around 6.25. All right. Yeah.
I'm sorry.
No,
I have
don't
one
apologize,
more
Carson.
quick question on a problem on the box plots homework.
Okay, before I go there, let me just
I might be able to ask you this verbally.
Carson, hold on. Give me a second. I want to wrap this one up first.
Oh,
So,
I'm sorry. I didn't know.
Okay. So let's just make sure. Are there any other questions about this? Did I at least address what you wanted? I forget who asked this. Was that you, Willie?
Yeah, I was just a little confused on the range rule of thumb as well.
Okay. Well, and seeing I hadn't talked about it, obviously, I wasn't aware that they were asking that. So, okay, cool. So let me go back to that question for you, Carson. So go ahead. What?
Number 3
Okay.
is the problem on box plots.
Okay, I'll pull it up, but why don't you tell me about it?
It's got 2 box plots. It's asking, it's 2 salaries for 2 different, I guess, different professions. And it's asking, so it has a different quartiles, and it says this amount of people make in the range of $70,000 to $80,000 or to $90,000, and it's asking what percentage of this work group is making less than the other work group.
Okay, so you're basically trying to determine which intervals are, say, bigger or smaller.
Yeah.
Okay. All right.
So it's like
You said it was number 3.
Yeah.
Let's see if my number 3 looks kind of similar to yours. Okay, yep, definitely the
It's
same kind
exact
of.
same question, actually. Almost the exact same question.
Okay, so here are our salaries for CPAs and actuaries. So again, think about how to interpret these box plots. So if you look at this first one, the CPA, this says that the minimum salary for a CPA is going to be probably around, what's that, like 33,000, let's say. That's about a third of the way between 30 and 40.
Yeah.
So around 33,000. The first quartile is at about 40. The median is at about 55. The third quartile is at 80. And then the max is at 91 or 2 or something like that. And if we look at the actuary box plot, it's actually got 4 of the same numbers. They're just at different places. So like the first quartile for the CPA is now the minimum salary for the actuary. The median for CPA is quartile 1 for actuary. Q3 for CPA is the median, and so on. Okay, so it says if a person is making the first quartile salary for a CPA. All right, so what value is that?
I'm sorry, can you say that one more time? I missed it.
If a person is making the first quartile salary for a CPA, how much are they making?
For CPA, $40,000.
Okay, cool. So it's around $40,000. So it says then this earning is equivalent to what salary for actuaries? So what salary is this for
The minimum.
actuaries? That's the minimum. So we'll put, that's the same as the minimum. All right, and so then the CPA is making less than what percent of the actuaries?
That's what I don't know how to do. I know like CPA is making what percent? So they're making less money at 90. So basically actuaries will make about $10,000 more at their maximum, right? Is that?
No, okay.
I just don't know how to find that percentage.
So we're talking about the person that's earning this much money, the $40,000.
Oh, okay.
On the actuary chart, the 40,000 is the minimum. So how many actuaries get paid more than 40,000?
0. Or 100.
Yeah. Yeah, it's the other side.
All of them?
It's all
or like
of them,
total.
right? So I mean, actually the people that are earning the minimum, the actuaries earning the minimum, they're not actually making more than this person. But I think that's a typo. I think they probably want to say making less than or equal to, and it's definitely 100%. Oops, not 1,000%. So if that CPA is earning just the first quartile, they're being underpaid or paid less than all the actuaries. So let's change this. Let's, instead of saying it was the first quartile salary, let's say it was the median salary. So if we look at the median salary for CPAs, that would be the first quartile for actuaries. So what percent earn more than the median for CPAs?
Earned more?
It would be, yep, it would be
like
75%. Because each of these chunks is 25%.
Oh.
Right?
Okay.
25% of the data lies in each of those things. That's why these work out the way they do. Because then we can really read it. So like, even if you're the highest paid CPA, 25% of actuaries are out earning you. So
okay.
If you were a CPA and you looked at this chart, you'd go, oh, this sucks. I'm in the wrong job. I need to become an actuary. And actuaries look at this chart and go, yeah, that's right. We earn more money.
Only some do.
In general, you do, though.
In this case.
In general. Yeah, not all do,
okay.
right? Obviously, yeah. The highest paid CPAs earn more than the lowest paid actuaries. But if you kind of went to an equivalent position, if you go, hey, I'm in the top 10% of actuaries, I earn more than the top 10% of CPAs. For sure. Looking at this data.
All right.
So
Thank you.
yeah, you're welcome. All right, so I'm going to go ahead and stop sharing here. And hopefully that was a decent little review of homework and stuff we've been talking about, because we do need to know those things as we move forward. And hopefully you're getting a little bit more comfortable with all that stuff. While I'm here, I just want to remind you again about that project, because the project does want things like box and whisker plots and some of this other stuff. I'm just bringing it up again because that due date's going to come up quicker than you think. So if you haven't already started thinking about a project and forming your little groups, now is the time to do it, because the due date for project 1 is a week from Thursday, January 28th. I know when we first started, January 28th felt like it was really far away. It's not so far away anymore. So you really should start looking at that, trying to form your groups and figuring out what kind of question you want to ask people so that you have time to collect that data and then actually do the project. Okay, so we'll talk more about that project for sure next time. But I want you to start thinking about what you want to do, all right, because that time is coming sooner than you think. All right, so I'm going to go ahead and hop up to the whiteboard. I'm going to switch screens here, and I'll be right back with you. All right. So I don't know if anybody saw, Allie just put in the chat box, she's looking for a group. That's a great way to start trying to get a hold of each other. Use the chat boxes, use the, you can message each other through Canvas, stuff like that, just to start forming groups. So anyway, start talking with each other and maybe you can start building some groups. Anyway, so let's talk just a little bit more review about what we did last time, some of the differences between mean, median, mode, how we calculate standard deviation, all that. I just want to make sure you got that down before we go into probabilities. So we already kind of talked about a little bit about some of these in the homework, but we'll go ahead and just sort of make this, we'll formalize it again. So measures of the center. The three big ones we use are mean, median, and mode. So just to remind you, the mean, this is the average. So it's the average of all of the data. So like in that example that we were just looking at with those numbers where we tried to find the range and the mid-range and all that, if you were to add up all those numbers and divide by how many there were, that's your mean. Okay, so it's the average of all the data. The median, this is the midpoint of the data list. So if we've got it all ordered, smallest to largest, the median is the midpoint. So it's either the middle data point or it's the average of the two middle data points. Okay, so that's the midpoint. And then the mode, this is the most frequent. And it can be that these are all the same. They can all be different. And really depending upon how the data is distributed, that's how these things will change. A great example that we actually did in this class. If you remember when I asked that, the age of first-year college students in the class. And if this isn't exactly the data set, we'll call it the data set. I think there were 5 of you that said that you were 18 and one that was 17, one that was 19. But let's say we have this list. Let's talk about mean, median, and mode. Okay, so first of all, what's the mode of this list? What's the most common answer on that list?
18.
It's 18. All right, so looking at this nice and fast and easy, we need to know that the mode equals 18. So I'm just going with that one because it was easiest. What about median? What's the value that's right in the middle? So if we look, we've got 7 data points. So the one that's right in the middle is right here. So this one, that's our median. Now it turns out the median equals the mode here. Okay, that happens. So, all right, so in this case, the median is 18. If we wanted to start doing like quartiles and stuff like that, we could do this as well. Why not? Let me just show you this. If you look at the quartiles, okay, so the first quartile has to be the median of the top half. Well, the median of the top half is 18 again, so there's our Q1. If you look at the bottom half, the median of that was Q3. So this one would give us a really, really boring box and whisker plot. Why is that boring? Can you picture it? Because think about the box, right? The box goes from Q1 to Q3. Q1 and Q3 are the same numbers, so this box has no width. There is no box. Even though there's a ton of data, there is actually no box. So this one would not be one where you'd want to use a box whisker plot. All right, well, there's our mode and our median. Let's get our mean. So what we would need to do is add these all up. So I'll put a plus here, right? So that we add them all up. So 17 plus 18 plus 18 plus 18 plus 18 plus 18 plus 19. Let's be smart about it. We have 5 18s. So 5 times 18, that's 90. Plus 19 is 109. Plus 17 is 126. So that's the total. And then we would need to divide that by 7. Well, if you take 126 and you divide by 7, you get 18. So when I ask you guys that question, and I literally just asked you that question for to have some numbers to begin with, I had no idea that you guys were going to give me such a wonderful data set. Because this is a great example of one where the mean, median, and mode are all exactly the same number, which is very rarely the case. Basically, what this tells me is there's not much spread to the data at all. And clearly you can see that. All right, so those are our 3 measures of center. And then the other thing that we're interested in that we want to calculate is the spread of the data. So we'll put here a measure of the spread of data. So the one that we primarily use is standard deviation. And how we calculate it depends on if it's sample standard deviation or population standard deviation. So when it's just plain old S, this is sample. And it's the square root of the sum of the xi minus x bar squared. Do you remember what x bar means? What is x bar?
Sample mean.
Good, that's the mean. So it's the mean of the sample. And then the xi, that's just the specific values. And then we divide that all by n minus 1. And n was your sample size. All right, so that's how we get the sample standard deviation. If we want the population standard deviation, that's sigma, kind of that squished 6. So this is population. And it looks very much the same. Except now we've got mu, that's kind of this m guy, and this is the population mean. And then n is the population size. So it's slightly a different formula. We're talking population versus sample. All right, so let's take this data set and let's calculate the standard deviation. So you guys, in your response to the ages of first-year college students, that was a sample. So we're going to use the sample formula. So what we need to know is the sample mean. Cool, we got that. And now we need to calculate the square of this difference for each one of those data points. All right, so here's what I'm going to do. Just make a little chart out of this. So here are different data points. Let's look at the xi minus x bar. So we're going to take our value, our data point, and we're going to subtract the mean. So for the first one, 17 minus 18 is -1. 18 minus 18 is 0. So all of those guys get 0. And then 19 minus 18 is 1. So we just take the difference between our data points and the mean. Then we're going to square all of those. So we'll make a column here that's xi minus x bar squared. Well, these are really easy numbers to get. Squaring 0 gives you 0, squaring 1 and squaring -1 both give you 1. So the standard deviation, if we put it into the formula, the sample standard deviation here, it's going to be the square root of the sum of all these numbers. Well, that adds up to 2. And then we need to divide by n minus 1. So the sample size, there were 7 in our sample. So 7 minus 1 goes right there. So this is the square root of 1/3. So that's going to be root 3 over 3, which is like 0.588, I think. I'm totally guessing on that though. I don't have my calculator handy, but I think that's what the square root of 1/3 is. For some reason, that number's ringing a bell. All right, so there's how you could actually calculate this thing. And remember what standard deviation tells you is how far stuff is spread out. The bigger standard deviation is, the more spread out your data is, the smaller this number is, the less spread out it is. And so since this number is small, 0.5, because remember what this is saying in terms of standard deviations, if we go 2 standard deviations on each side, no matter what, we're guaranteed to have at least 75% of the data. So if I was to go roughly 1.2 away from the mean on either side, so 18 plus 1.2 and 18 minus 1.2, I'm going to catch at least 75% of the data. In this case, I catch 100% of the data. I don't actually have to go very far. Okay, so that's basically the idea behind this. So really what we want to know is how many standard deviations away we are. So that's really the question. When you have a data point, you want to see how far is it from the mean. Is it close to the mean? Is it far away? And really the measure of that is standard deviations. So I didn't mention this last time, but let me go ahead and share this with you now. We also, another number that we attach to data points is what we call the z-score. And the z-score, there's a formula for it. And it goes like this. You're going to look at how far away you are from the mean. So you're going to calculate the difference between your data point and the mean. And you're going to divide it by the standard deviation. So what I've got here is if this is a sample z-score, you could also do a population z-score that changes the x bar to a mu, changes this to the sigma, to the population standard deviation. But really all this is doing is it's telling you how many standard deviations away you are. All right, so it's the number of standard deviations from the mean. So if we start getting to be lots of standard deviations away, we start knowing it's an outlier. It's an unlikely number, right? And we saw, like when you look at Chebyshev's rule or the empirical rule, we have a way of knowing what kind of z-score is a big z-score or a small z-score. So for example, let's look at the 17. All right, so our minimum number. Let's find the z-score for 17. For the 18s, their z-scores are all 0. Actually, make another column here. Another column. And we'll put z-score. So all of those guys, all of you that are 18 or answered 18 with the age of the first year college student, you guys all have a z-score of 0 because you're at the mean. So for any of you that are that answered 18, you are very much near the center of the data. You're not outliers, not for this sample. Now, we don't exactly have a lot of spread, but let's see what happens with the 17 and the 19. I'll actually start with the 19. So for the z-score for the 19, that's going to be z equals 19 minus 18 divided by s. So we're going to divide by that 0.588. So it's going to be 1 over 0.588. And I want to say that's like 1.76.
It's 1.700.
Oh, okay. All right, so that means that that data point is 1.7 standard deviations from the mean. 1.7 is not very big, right? We know that if you are within 2 standard deviations, you're within the middle of the 75, you're within the 75% of the data. So yeah, that's reasonable. So if we did the z-score for the 17, it's exactly the same computation, except we put a 17 instead of the 19. And check this out, that just makes that a -1, which just makes that a negative 1.7. So a couple things. First of all, still a small number, 1.7-ish. It's not very big, but it's negative. Well, that tells you something. If your z-score is negative, that means that you're below the mean. Okay, so z is less than 0, you're below the mean. If your z-score is greater than 0, you're above the mean. So that's something really important when you read a z-score, because it's going to tell you, oh, is this on the smaller side or is it on the bigger side? And it also, the magnitude of it tells you how far away you are. So you may be wondering, why do we actually care about z-score? Right? I mean, yeah, it tells us how far away it is. Well, you can actually use this to compare 2 different things. Like, let's say we were looking at apples. All right, and we go to Rayleigh's, to your local grocery store, and we go and we collect all the Fuji apples and we weigh them. Okay, so we weigh each of the Fuji apples to get their masses, and then we do the statistics on it. So we take that data set, we find the average, right? We find the mean, we calculate the standard deviation, all that good stuff. And then we do the same thing with the Gala apples. Okay, so we take all the Gala apples, do the same thing. And then we go and we take a representative apple from each, and we want to compare them, and we want to know which of them is actually like compared to the average apple of their type, which one is bigger, right? Which one is, deviates more from the mean. We couldn't necessarily just look at the weight difference, because not all apple types are the same, but we could calculate the z-scores. And maybe for that Gala apple, we calculate a z-score of 1.5. And then for our Fuji apple, we calculate a z-score of 2.8. Well, the fact that z is 2.8 is bigger, that means that that apple is further away from the mean. So it's a more unusual apple or uncharacteristic apple than the other one was. So we use z-scores as a way of comparing 2 different kinds of quantities, 2 things that are coming from different sets, but calculate them relative to their specific means and standard deviation. Anyway, so if you run across z-score, when you run across z-score, this is what it is. All right, so these are the 2 big things we measure. Where's the center of our data? And what's the spread? How far do we go? How far does this data spread out? All right, so these are things that we need to know so that when we start doing studies, we can start seeing how do we actually analyze our data. But there's another big piece to this that we need in order for us to actually calculate things and understand what's going on. And we need to talk about probabilities. So that's what I'm going to dive into here next. But let's take a real quick break. It's 4:51 by my clock. Let's take 5 minutes. Give me a chance to go get a drink and use the restroom. And we'll start back up. So you know that you're going to know that I'm ready to go when you see this picture again. Okay, so come back in like 5 minutes and we'll start talking probabilities. All right, so let's talk probabilities, but real quick, just to share, I don't know if you guys caught it, Star Wars shirt of the day, a little homage to my favorite painting, Starry Night by Vincent van Gogh. Yeah. Anyway. All right, so let's talk probabilities. Now, you might have an idea of probability. We hear that word all the time. We use that word. But let's formalize it a little bit when it comes to statistics and math and what we're actually doing. Okay, so first of all, when we talk about probability, if we're going to relate it to what we've talked about, this is the long-term relative frequency of an event. So I'm going to be a little generic here. So an event can be anything. Paradise and rolling a 7, that's an event. Drawing a card out of the deck and getting an ace, that's an event, right? A meteor smacking into Earth, that's an event, right? An event can be anything. But probability is the long-term relative frequency. So we already know about relative frequency, right? Relative frequency is the, if we look at the frequency of that event, divided by all the possibilities, that's relative frequency. But I put on here long-term, and this is kind of an important thing when it comes to probability, that when we talk about probabilities, these are likelihoods, chances, whatever. This thing will happen if we repeat this experiment, if we repeat the trial many times. All right, because any one event, the probability of an event one time is not necessarily the long-term relative frequency, because chance is involved. Right? Probabilities are always things where things we call chance experiments, which are things where the outcome isn't known. But probability gives us a benchmark. It gives us an idea of what to expect. What's the likelihood of something happening over the long term? Okay, so some terminology or some the symbols that we use for this. If we call our event, say A, capital A is a pretty common way of describing an event. We also use capital B a lot, but you can use anything. But if we want to talk about the probability of an event, we're going to write this. So the capital P literally means probability. And then the A is our event. So literally, this is the probability that event A occurs. So that's how we read that, right? What is the probability of A? P of A. All right, so let's talk about some specifics, because I think it will help if we look at some specific examples so that you kind of understand the idea behind probabilities. So I know I used these last time. I got a deck of cards. And you may not know a lot about a deck of cards, but I'll definitely give you all the information that you need for us to do probability. So first important thing to know is that there are 52 total cards. All right, so if you take, count up all the cards in the deck, there are 52 of them. They are broken down into 4 suits. You have spades, which are these ones that look like black hearts with a little tail on them. Speaking of hearts, you've got hearts. You've got clubs, which look like little puppy dog feet. And then, of course, you have diamonds. Let me find a diamond, which look like diamonds. Okay, so you've got hearts, clubs, spades and diamonds. There are 13 of each. So if you take 52 and you divide by 4, you get 13. So there are 13 of each one of those suits. Just so you know, because we'll be doing a lot of probabilities involving these. The other thing that we often use are for any one denomination, like this 4, and this is the 4 of hearts. There are 3 other 4s in here. There's a club, a heart, or a diamond, and a spade. So there's always 4 of each. And then the other designation we use are face cards. And the face cards are the ones that actually have people on them. They are kings, queens, and jacks. So you can see I got a king, queen, and a jack. Those are the face cards. So there are 3 of each suit. So there are 12 of those. Anyway, just so you know. Now, let's talk about probability. So I'm going to shuffle up the cards. And what I'm going to do is I'm going to draw one card. Draw one card. And here's what I want to know. If I randomly draw a card, what's the likelihood that this card is a face card? All right, so what is the probability that it's going to be a face card? Now, it won't always be a face card, right? Like I already peeked. This one's not a face card. All right, so I drew one at random. I did not get a face card. All right, so let's do that experiment again. Did I get a face card? Nope. Okay, so I do that experiment again. Shuffle up. Get a face card? Nope. All right, so it's seeing it's not happening very often. Does it mean it's impossible? No, because eventually I'm going to get one. No. Nope. Hey, okay, so there you go. So I got a face card. So what I would be doing if I wanted to calculate this probability is basically keeping track of every time I get a face card versus every time I don't. And I would keep track of my relative frequency. Right? So I don't know how many times I just drew there. Let's say it was 10. And out of those 10 times, 1 time was a face card, right? So the relative frequency at this point is 1 out of 10. All right, well, 2 out of 11. 3 out of 12. Oh my gosh, I'm on a roll. 4 out of 13. 4 out of 14. 4 out of 15, right? And I just keep going like that. The probability is the long term. If I were to keep doing this hundreds of thousands of times, like I just keep drawing and shuffling until I fall over dead, that number, that relative frequency is going to get closer and closer to the probability. All right, well, obviously I don't want to draw these things and keep doing this experiment until I die. All right, it's impossible to do it forever. So instead, we can calculate the probabilities in actually a fast and easy way. All right, so here's what you do to calculate the probability of A. This is the number of outcomes that produce A divided by the total number of possible outcomes. All right, now when I talk about an outcome, let's go to the context of the cards. An outcome is the card that I draw, right? So I draw the card. This is one of the outcomes. What is it? The 9 of hearts. It's one of the possible outcomes, and that's the one that I got. Here's another outcome, Jack of diamonds, right? And so on. So if I wanted to calculate, say, the probability of getting a face card, I need to know how many of these outcomes produce a face card. So basically, how many face cards are in the deck. And then I need to know how many total possible outcomes are there. How many total cards in the deck. All right, so here's how we would calculate that for this one. All right, we're going to let A be draw a face card from a deck, from a standard deck. Okay, so here's our probability. First of all, the total number of possible outcomes is 52. There are 52 cards in here. Any one of them is just as equally likely to be drawn if I shuffle up and I'm truly random. So the question is, how many of them are face cards? Well, I don't know if you remember, but there's a queen, king, and jack for each of the data sets, or for each of the suits. So there are 3 face cards that are hearts, 3 that are diamonds, 3 that are clubs, 3 that are spades. So there are a total of 12 of those. So the probability that when I reach in here and I grab a card, probability that's a face card. Hey, all right. Probability that that happens is 12 out of 52. Now I'm going to go ahead and reduce this down, mostly because I can. And this ends up being 3/13. So 3 out of every 13 draws, on average and long term, are going to be a face card. All right, so I don't know if you remember, but as we were kind of going and I was keeping track, and I said, well, I got like 1 out of 10, and then, oh, like, no, there's 2 out of 11. At one point, I think I was 4 out of 14, which is pretty close to this actual number. But again, only drawing 14 times is short term. Okay, but roughly out of every 13 draws, 3 times I should get a face card. Now, does that mean that sometimes I won't? Sure. Sometimes if I draw 13 cards, I only get 2 face cards. Maybe I get 6 face cards, right? Who knows? But over the long haul, this is our likelihood. So this is how we calculate probabilities. It's just the number of outcomes that produce what we want divided by the total possible number of outcomes. You'll see them as reduced fractions. You also see them as decimals. You'll also sometimes see them as percents, right? The probability of something happening is 27% or whatnot. But this is how it's calculated. All right, so some things about probabilities. First of all, probabilities are always between 1 and 0. So no matter what our event is, I don't care what it is, like, yes, this was drawing a face card, but no matter what your event is, the probabilities are always between 0 and 1 inclusive. It is possible to get a probability of 0. It's also possible to have a probability of 1. But you can't have a probability bigger than 1 or less than 0. If your probability equals 0, this means that the event cannot happen. So if you ever get a probability of 0, that's something that never happens, ever. Probability of 1 means that your event is guaranteed. All right, so that's the range. And as we get closer to 1, it means it's more likely to occur. If we get closer to 0, it means it's less likely to occur. So it's a sliding scale between 0 and 1. 0 never happens. 1 always happens. When we're somewhere in the middle, if we're at 0.5, that's the toss-up. It could go either way. If we're greater than 0.5, we're much more likely to occur. If we're less than 0.5, we're less likely to occur. All right, so like probabilities that are 0, me giving birth. The probability of me giving birth to a child, 0, because I don't have the right parts. I don't have a uterus, so it's not going to happen. right? A probability that's 1, I can guarantee is going to happen. I will die. If the event A is Bruce dies, Bruce dies at some point, that probability is 1. I'm going to die at some point, right? So there are certain events that for sure have a probability of 1. There are certain events that for sure have a probability of 0, but there are others that have random probabilities. What's the probability that tomorrow when I'm walking my dog, I see a bald eagle flying by? All right, is that probability 0? No. There are bald eagles. They do fly around. I do walk my dog, right? So there's potential that they match up. Is the probability 1? Is it guaranteed that that's going to happen? Nope. Right? Definitely not. So it's somewhere between 0 and 1. I would put that probability kind of on the low side. Although I did see a bald eagle not that long ago flying around. There are not a lot of them around here, especially right this time of year, although they're starting to come back. I don't know if you guys know this, but in the Carson area, you come down the hill from Tahoe, the bald eagles like to come down there in like February and March. So you'll start seeing them a little bit more if you start looking for them, if that's your kind of thing. But anyway, so this is the idea behind probabilities. Okay, now, probabilities of single events are great and all, but sometimes we want to look at probabilities of two different events occurring at the same time, not occurring at the same time, and so on. So I got to give you some more information here, some more details here, some more definitions. So the first is, what does it mean if we're talking about probability of A and B? So A and B are two different events. Maybe A is drawing a face card and B is drawing a heart, let's say. Okay, so those are two different events. So the question is, what does and mean? All right, now in the context of math and logic, and means both occur. So if you ever see probability of A and B, that means both of them occur. The other word that we use to combine these things is or. So we could have probability of A or B. Okay, so what or means is one or both. Let's do it this way. Say A occurs or B occurs or both occur. So and, the word and is restrictive. It's much harder for and to occur because you have to be part of both events. Or is less restrictive. It's more likely for an or to occur because not only is it going to happen if A were to be the result, but also if B is the result. So there are more options. So let me show you how this works again with cards. We'll talk about some probabilities here with a deck of cards. And we'll talk about and versus or. So for this example, here's what A is going to be. A again is going to be draw a face card. But B let's make B draw a heart. So before we actually do the probabilities, I want to show you what's in all the different sets. All right, and so we call this a sample space, but this is what A has in it. You can have a king of hearts, a queen of hearts, or a jack of hearts. You can have a king of diamonds, a queen of diamonds, jack of diamonds. You can have a king of clubs, queen of clubs. You can have a jack of clubs. And then you can also have the spades. So you can have the king of spades, the queen of spades, and the jack of spades. So those are the 12 outcomes of A. Those are 12 outcomes that give us A. All right, now in terms of the hearts, here's what that set looks like. We have ace of hearts. I'm not going to draw the hearts because I'm tired of drawing them. But you have the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king of hearts. So those are all the different cards that produce that. All right, so before we get to and or, we already saw what the probability of a face card was. Right, that was 12 out of 52, which was 3 out of 13. So the probability of a heart, we count up how many different options we have for hearts. There are 13 of them. Out of the total was 52, which reduces to 1/4. So roughly 1 out of every 4 draws, you're going to get a heart. So drawing a heart is a little bit more likely than drawing a face card. Not a lot, right? 13 out of 52 versus 12 out of 52. All right, but now let's talk about and or in this case. So let's start here. Let's look at and let's make our sample space for A and B. So what we want is a face card that is also a heart. So for and, both of them have to have it. All right, well, how many different possibilities do we have of a card that's a face card and a heart? Well, it's not many. It's just those 3. So in terms of this set is really small. There's the king of hearts, the queen of hearts, and the jack of hearts. Those are the only cards that are both face cards and hearts. All right, so the probability of this then, we are to look at what's the probability of A and B. Well, there are only 3 outcomes that match that out of the 52. So notice that this number is much smaller than either one of these. And that's what I meant by saying the word and makes it more restrictive. It's much less likely to occur when we talk the probability of A and B. Just give me a second here. I have to reduce this because it's driving me crazy. Oh no, 3 doesn't go into 52. Never mind. That is reduced. All right, so probability of getting a face card and a heart, not very likely. All right, so really what we're looking for when you have and is look for the overlap of these sets. These 3 cards are in both sets. So they are in A and B. All right, now, if we go to A or B, now I'm not going to write out the entire list because it's an awfully long list. But basically what we're going to do is we're going to take these two sets and we're going to stick them together. We're going to take all of the hearts and all of the face cards and we're going to put them together. All right, now to do this, or to show you what's going on, I am actually going to make use of my deck here. So I'm going to separate out all the hearts and all the face cards. So I'll just drop none of those guys down there. I can do this pretty quickly. All right, so I now have both sets here in my hands. I've got all the hearts and all the face cards, and I've even got them separated out here. So you can see here all my hearts. So there are the 13 hearts. That's that bottom set. All right, so let me just set those down, and then I'll show you my face cards. So that's that top set. Now, what you may not have seen me do is that when I went and I had to switch the king, queen, and jack from one set to the other set because these are the elements that are part of the and. All right, now when we go to the or, I just put all these cards together. So this is the set of A or B. So it's all the face cards and all the hearts put together. But I want to point something out. Notice this king, queen, and jack. Those were both, they were on both lists, but they only show up one time in this set. We don't repeat things. If you have an element that's, or an element that's in A and in B, it only shows up once when we stick them together. We don't write the king of hearts twice because there weren't two kings of hearts in here. There's only one. All right, so this list, A or B, this is all face cards and all hearts. So we just lump them all together and we're right there. Okay, so if we want to know the probability of A or B, well, again, there are 52 total cards in this deck. But the question is, how many of them will either be a face card or a heart? Well, I can count them up. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And there's 22 of them. So this is 22 out of 52. But let me show you a faster way of getting that value if we know how many are in each of these. So I don't know if you remember how many were in each, but for A, there were 12 of them. And for B, there were 13. If you want to get the total, here's what you do. You take the number in A and you add it to the number in B and you subtract the number that are in A and B. So there were 12 in A, 13 in B, but there were the 3 that overlapped. So we take those away, and believe it or not, there's our 22. So there's a faster way, just from me to you, if you want to try to calculate one of those things, or count those things without actually having to count them. If you know how many are in each, you add up the two individually and you subtract off those that are in common. We have a really fancy name for that. It's called the principle of inclusion and exclusion. Sure. But really, it's just the reason we take off those that are in common to both is they got double counted. When we just added A and B, the king, queen, and jack of hearts got counted twice. So we have to take care of that. All right, so this is way more likely. You look at those other probabilities that were 13 out of 52 and 12 out of 52. This is now 22 out of 52. It's much more likely that this is going to occur. All right, so and or, two very small words, two words that don't really seem like they're a big deal, but they are a huge deal. They are an absolutely huge deal because they change completely what's going on. So you got to pay very close attention to those words. All right, so some terminology for you. We have what we call a complement. All right, so the notation for this, I'm going to say complement of A. So A is an event. The complement is written like this, A with an apostrophe. Sometimes in words, this will be called A prime. You'll definitely hear me say that because we use this in calculus as well. So this is A prime. And the complement of A, this is all of its not in A. So it's all the other possible things. So in the context of ours, where A is face cards, the complement is not face cards. It's that easy. Or B was hearts. The complement of B is not hearts. Anything but a heart. Okay, so complement, that's all this means. Now, when it comes to probabilities, kind of interesting thing about this is that if you were to take the probability of A and you were to add to it the probability of its complement, so the probability of A plus the probability of A prime, this always equals 1. And that might feel a little bit weird, and you might be wondering why that is. But if you think about it, it should make sense. Come back to that face cards versus not face cards. What's the probability that when I draw a card from the deck, that I get a face card or not a face card? 100%. It's going to happen. Right? Oh, look, I didn't get a face card. That's not A. Oh, look, I got a face card. That is A. No matter what I draw, it's either a face card or it's not a face card. So, turns out that with complements, probability of a complement plus, or probability of A plus the complement of A is always equal to 1. All right, so that's complements. Another kind of probability that we've got is what's called conditional probability. So in words, what we would say for conditional probability is, what is the probability that A occurs given that B has occurred? All right, so conditional probability means that we already know something happened. And conditional probability, so now it's the, well, what's the chance of our event happening knowing this already occurred? So in symbols, what this is going to look like, you're going to have the two events, A and B, and they're going to be separated by a vertical line. Read that vertical line as the word given. Okay, so given that that's already happened. All right, so let's go back to our face cards and hearts idea. All right, so I still have all those cards kind of separated, my face cards and my hearts. And remember that A was face cards and B was hearts. All right, so if we go back to that example, let's talk about the probability of A given B. All right, so this is how to think about it. And this is why I like using cards, because I can actually model it with stuff in my hands. So we're going to be given the fact that we have drawn a heart. Okay. B, the second letter, has occurred. So I have drawn a heart. So here are all the hearts. At least I hope I have all the hearts. And so if you look at them, you can see that I got all the hearts. So now the question is, what's the probability that if I already have a heart, that when I select a card, it's a face card? So what we're going to do when we calculate this probability is the same as every other time, where we count up the number of outcomes of our event, which is face card. So looking at these, all the hearts, how many of them are face cards? Well, there's the three of them, right? King, queen, and jack. So the number of outcomes, right, face cards is 3. All right, but then it has to be out of the total number of outcomes. Now, I'm not going to use 52 anymore because I don't have 52 cards. I'm already restricted to the fact it's just a heart. So if I just count these up, I count there's 13 of them. So the probability of getting a face card, drawing a face card, if I already know I am down to just hearts, given that hearts have happened, is 3 out of 13. All right, so that's what conditional probability means. It means that something's already happened. There's already a limitation. I'm down to just the hearts. And now we perform our experiment. It's very important to recognize that these probabilities, the order matters. So let's do the same, but let's look at the probability of B given A. So now what that means, I want to look at what's the probability that I draw a heart if I already know that I'm down to just face cards. Okay, so I already know I have just the face cards. What's the probability of drawing a heart? All right, well, again, we need to look at this set and see how many of them are hearts. Well, it's still 3. Still the king, queen, and jack of hearts. But the question is, that's 3 out of how many? How many cards are actually in here? Well, there's 12 of them. There's the king, queen, and jack of each of the 4 suits. So we're actually out of 12, which is 1 out of 4. So there's a 1 out of 4 chance that when I draw one of these cards at random, it's going to be a heart. These are not the same. Those are different probabilities. So when we look at conditional probability, not only does it matter what the two events are, but it also matters in which order the events are occurring, which one is already given. That one definitely matters. All right, so that's conditional. A couple more terms, and then we'll talk about how we can do these calculations faster, because we don't want to have to always count, right? You don't want to have to every time count up how many of each thing and all that. And there are faster ways. I got to give you a couple more terms here. So the next one I want to give you is what we call independent. All right, so independent events. We say that A and B are independent if one does not affect the other. All right, so if one event occurs, it doesn't change the probability of the other event. Okay. So that's what it means for them to be independent. One of them happening doesn't affect the other. All right, now in terms of the formulas and stuff like that, basically what this is saying is that the probability of A, given that B has already occurred, is the same as just the plain old probability of A. Right? B does not affect A. And similarly, the probability of B given A is the same as the probability of B. Okay, so the first one here is saying B does not affect A. The second one is saying A does not affect B. So this is what it means if they're independent. One does not affect the other. So here's an example of two events that are independent. Let's say one of the events is drawing a heart from a deck of cards. So I've got my complete deck and I'm drawing a heart. The second event is rolling a die and getting a 3. Now, those two you can see are pretty much obviously independent. Whatever I roll on this die doesn't affect me drawing this card at all. So those things are clearly independent events. But what about our two events as we had written? The getting a face card versus drawing a heart. Because now you might go, well, there's a chance that they're dependent, that I took a heart affected my probability of getting a face card. Or the fact that I've got a face card, maybe that affected the probability that I'm getting a heart, right? So sometimes it's not obvious if things are dependent or not. And so really, if you want to check to see if things are independent, you look at these. You look at what is the probability of A given B and the probability of A. Are they the same? Is the probability of B given A the same as the probability of B? And if they are, these are independent events. If they aren't independent, we say that they are dependent. So not independent is called dependent. So two events are either independent or dependent. And so the question is, which is which? All right, now, one way or one thing that I can tell you for sure will make it so that you have dependent events is if we go back to replacement. You remember sampling with replacement versus without replacement? Yeah. With replacement means we sample and then we put that back in before we sample again. That's with replacement. Without replacement is we take our sample, we don't return them before we sample the second time. I mentioned like catch and release as an example of with replacement. With cards, with replacement would be we draw our card and we put it right back in. Shuffle up, draw again. Without replacement, I draw my card, then I draw another card. Well, it turns out that if you do replacement, so sampling with replacement, or sorry, without replacement, so we take a card and we don't put it back in. This is always dependent. You're always going to get a dependent relationship because you're changing the probability by not putting it back in. Like, let's just go back to, I'm drawing a card and I want to know, is it a heart? I've got 13 out of 52. If I don't replace and I draw again, now I'm going out of 51. So I'm going to get a different probability. All right, so sampling without replacement is always going to lead to dependent. Sampling with replacement may or may not. It depends what we're actually doing. But this is definitely a place where we get dependent in terms of stuff we've already talked about. Okay, so that's independent. So one more, I just got to give you one more and then we'll get to some formulas. And this next one is what we call mutually exclusive. And so A and B are mutually exclusive if they both can't occur. All right, so two events are mutually exclusive if it's not possible for them both to occur at the same time. So let me give you a pair of events from drawing cards that are mutually exclusive. So let's say A is drawing a black card. So a club or a spade. And B is drawing a diamond. All right, so it's possible for me to reach into my deck and draw a black card. It's possible for me to reach into my deck and draw a diamond. But it's not possible for me to reach in, draw a card, and have that card be both black and a diamond. Because none of the diamonds are black. They're all red. Okay, so that's what it means for A and B to be mutually exclusive. It means they both can't occur at the same time. Well, just like with independent, mutually exclusive, we know something about probabilities here, and that's this. The probability of A and B equals 0. Remember what 0 meant as a probability. It's impossible. And meant that you're in both of them. So mutually exclusive means the probability of getting both at the same time is 0. Okay, so that's what it means for things to be mutually exclusive. All right, so let me just wrap up class with a couple of formulas for you to help you when you're trying to deal with or and it will come into all this mutually exclusive and stuff like that. Okay, so first, if you want to calculate the probability of A and B, so these are probability formulas. So this means that we are in both, that both event A and event B occurred, right? That's A and B. This is equal to the probability of B times the probability of A given B. And I'm going to put an or here because there's a second form of this. It would be the probability of A times the probability of B given A. So this is called the multiplication rule of probabilities because we're multiplying probabilities. All right, but this is how we get a probability of A and B. Before I show you the next one, though, I just want to point out that check out what happens if they are independent. If they're independent, these conditional probabilities were the same as just the probabilities of the first one. And so we like independent events because it's really easy to calculate the probability of and. You just multiply the two separate probabilities together. So that's just a special case. If they're independent, all you got to do is multiply their two probabilities together. All right, so there's the formula for and. There's also a formula for or. So we'll have here the probability of A or B. So remember, this is the one that's less restrictive because you can be in A or B or both. And it's found this way. It's the probability of A plus the probability of B minus the probability of A and B. And we did this a little bit. You may remember when we did the and example of the, the or example with the hearts or face cards. We added up all the hearts, we added up all the face cards, we added those together, but then we subtracted those that are in common. Well, that's what this is. This was probability of heart or face card. Probability of heart. The king, queen, and jack got added twice, so we had to take those away because those were the overlap. So this is called the addition rule of probability. Duh, because we're adding. All right, now we also get to have a little bit of, oh yeah, but check this out. If A and B are mutually exclusive, so remember, mutually exclusive means they both can't occur at the same time. That means that this probability of A and B is 0. And so if you're in a situation where they're mutually exclusive, you get the OR probability by just adding up the two individual probabilities. So these are the formulas you're going to want to use to kind of expedite the process. If you know the individual probabilities, you can build the probabilities of and or and all that if you know some other things about them. And what we'll do next time, because we definitely don't have enough time today for this, next time we'll do this. We will take some probabilities and we will do all kinds of calculations with the ands and the ors and the conditional, just so you can get the practice. But that's what we'll do starting off on Thursday. All right. But I do want to remind you that there's also another quiz coming up on Thursday. The first quiz was just on chapter 1. This second quiz is going to be on chapter 2. So on Thursday, there'll be a quiz on chapter 2, which is all about mean, median, mode, standard deviation, all that kind of stuff. It'll be just like last time. It'll be available to you starting at 3:30. It just needs to be uploaded by 4. We'll start Zoom class at 4. All right. Also, don't forget homework. The first few sets of homework are due tonight at midnight. So you still got a little bit of time. Make sure you get in there, finish them up. And I forget who it was that asked me. I think it may have been Ashton. You can definitely go back and work on ones to help raise your score as long as you do it by the cutoff time of 11:59. Okay. So with that, I'm going to go ahead and stop our recording and wish you guys all a great couple days, and I'll see you on Thursday.